Okay, we are coming to the third speaker of this session. And when he ends, please don't flee immediately for coffee because there will be a short announcement. So, Ruben, please go on. Oh, I didn't say that he is going to speak about probability monads as codensity monads. Sorry. Now you can go on.
Yes, thank you. And thank you to the organizers to organize this event and to giving me the opportunity to speak. So I will talk about probability monads and how we can view those as codensity monads. So these are the things I plan to talk about. So I'll first give some introduction or motivation or more the philosophy behind the result. And then, as the title says, I'm going to use codensity monads. So I will say something about codensity monads. And then I will describe these four probability monads and tell what they are and how we can view those as codensity monads of some functor. Okay, so for motivation, so what is a probability distribution? So on a finite set, the probability distribution is easy to define. So we simply give to every element in our finite set a number between 0 and 1, such that they sum up to 1. So for example, a coin, we can give probability mass 1/2 to each side of the coin. Then for countable sets, we can do the same thing. So once you have convinced yourself that these countable sums make sense, we can do the same thing. And an example of that is the Poisson distribution. But in general, we want to talk about probability distributions on more general spaces and sets. For example, on sets such as the real line or function spaces to describe stochastic processes and so on. But then we cannot really do the same thing anymore because an uncountable amount of positive numbers won't converge. So then we need to add extra structure to our sets and use measure theory to get the usual definitions of probability measures. So the idea is to use these first two simpler probability distributions and extend those to the more general probability distributions. And to do that, we're going to use codensity monads. So I'll briefly recall what a codensity monad is. So if we have some functor g from D to C, such that the right Kahn extension along itself exists, then that induces a monad. So as end of functor, we take the right Kahn extension along itself. So that's why we need this condition. And then we use the universal properties of right Kahn extensions to define a unit and a multiplication. So for example, we have this natural transformational isomorphism, and then the universal property says there's this unique eta such that these diagrams are equal. And then you can show that this is a monad, and we call that the codensity monad of G. Then some examples of codensity monads. So if we have a pair of adjoint functors, and we take the codensity monad with the right adjoints, then that is simply the monad that's induced by the adjunction. And then a more concrete example, if we take the codensity monad of the inclusion functor of all finite sets in the category of all sets, that will give us the ultrafilter monad. So then the first probability monad, so that's the jury monad on the category of measurable spaces. So I'll first say what the jury monad is. So we're working with measurable spaces. So for a measurable space, curly X, we define this measurable space curly GX. And that's the space whose underlying set is the set of all probability measures. And then we give this the sigma algebra, the smallest sigma algebra that makes all these evaluation maps measurable. So that's all the evaluation maps for all measurable subsets of X. And then for a map of measurable maps, or measurable function, we can define a measurable map curly GF from GX to GY by pushing forward every probability measure along this F. So this is my notation for pushing forwards along F. And then this gives us a functor curly G from measurable spaces to measurable spaces. Then for every measurable space X, we also have this map eta X from X to Gx, which sends every element X in X to the Dirac delta. So that's a probability measure that's completely concentrated on the singleton X. And then you can show that this forms a natural transformation from the identity functor to G. And then we can also define a map mu X from GGX to GX. And what we do here is, so we have this probability measure on Gx, so on this probability measure on the space of all probability measure, and we make that into a probability measure just on X by integrating away one layer of probability or one layer of randomness. So that gives us a probability measure on X, and this also becomes a natural transformation. And then Giri showed that this is a monad, and we'll call it a Giri monad. So now I'll explain how we can see this monad as a codensity monad. So for that, I need to define another functor, and then we're going to take the codensity monad of that functor. So for a countable set, we can look at this subspace. So all these families or collections of numbers in 0, 1 such that they sum up to 1. So it's really all the probability measures on our countable set A. So I'll denote that by GA. So this is a normal G, not a curly G. And then for every map of countable sets, we have this map GF, which is given like this. So this is well defined, and this is really the same as pushing forward along F of the probability measure. So that will give us a functor from the category of countable sets to the category of measurable spaces, which I'll call G. And then, well, the result is that the codensity monad of G is a Giri monad. So I'll try to sketch the proof. So we want to show that curly G is the right-hand extension of small g along G. And for that, we use this limit formula of right-hand extension. So here U is the forgetful functor. So to do that, we'll first find a cone. So for every measurable map F from X to GA, so that's really an element in this category here, we can define PF, and that will send a probability measure P to the integral of F with respect to P. And then using results about integrals, we like monotone convergence and so on, we can show that this measurable space together with all these maps forms a cone over the diagram. So now what we want to do is show that this is a universal cone. To do that, we take another cone, so another measurable space with other measurable maps indexed over all these elements or objects in this category. And I'll first introduce a little bit of notation here. So that's the first bullet point. So if we have some measurable maps map from X to 0, 1, I'll use a notation F hats to mean the measurable map from X to G2, where 2 is a set of 2 elements defined by 1 minus Fx and Fx. So that's those sum up to 1. And then for every little y in our measurable space Y, we define this map Iy from set of all measurable maps from X to 0, 1 to 0, 1. And we define that by this. So F is sent to QF hats Y and then the 1 projection. So this one really refers to the element 1 in a set of 2 elements. And then we want this Iy to have good properties. So, and these good properties are going to be the following 2. So if we have a countable collection of maps, measurable maps from X to 0, 1, such that their countable sum, or their sum is also a measurable map from X to 0, 1, then this Iy preserves these sums. And we can also show that IY sends the constant 1 function to 1. So for this, we need the fact that these QFs form a cone over the diagram. So we have this IY with good properties, and then by a representation term of probability measures, we know that there's a unique probability measure, which I'll call PY on X, such that IY is really integration with respect to this probability measure. Okay, so for every little y in Y, we have a probability measure. So this defines a measurable map, or well, this defines a map which you can show is measurable, and then you can show that this is a morphism of cones, which is the unique morphism of cones. So that gives us the universal property. So that's the main idea of the proof of this result. So then some remarks. We could also have used only finite sets instead of countable sets. That would also give us something. So that would give us a finitely additive probability measures. And then this second remark is really about how we view probability measures. So in this proof, I really used this integration operator view of probability measures. So we could identify this right Canonical extension of G along itself as the functor that sends a space X to the space of all integration operators. But if we want to construct probability measures in a more direct way using right Canonical extensions, we could also have taken the right Canonical extension of G along J, where J is the functor that sends a set to the set itself together with the power set as its sigma algebra. And then I should also note that the jury monad is also constructed as a codensity monad by Tom Avery, which he uses the inclusion of the category of complex sets in measurable spaces. And then for the second example, so that's the Radon monad on the category of compact Hausdorff spaces. So let X be a compact Hausdorff space, then we'll call a Borel probability measure P on X Radon if we can approximate every PA with the compact subsets of A. And then I'll define the Radon monads. So curly Rx is going to be the space of all Radon probability measures now. And the topology is induced by all these evaluation maps. So for every continuous function f from x to 0, 1. So that sends a probability measure to the integral of f with respect to that measure. So then this defines, again, a functor. So the same on morphisms, pushing forward along continuous functions from compact Hausdorff spaces to compact Hausdorff spaces. And then the meaning of this topology is that it is topology of weak convergence of probability measures. So it has also a probabilistic meaning. Then for a unit and a multiplication, we do very much the same as before. Of course, now we need to check that everything is continuous and that this probability measure we obtain by this integral is again a Radon measure and so on, but that all works. So that will give us a monad, and we'll call that monads the Radon monads. Now again, we're going to define a functor and then we're going to take the codensity monad of that functor. But now we're only going to use finite sets. So let A be a finite set. Again, we look at all these probability measures on the finite sets, and we'll call that compact Hausdorff space RA. So this is normal R, not a curly R, and that will give us a functor from finite sets to compact Hausdorff spaces. And then the result again is going to be the codensity monad of R is the Radon monad. And the interesting here is that we only use finite sets, while Radon probability measures are sigma additive. And then a sketch of the proof. So let X be a compact Hausdorff space. So as before, this codensity construction, we can identify that as a space of all integration operators. And here's f plus g when f plus g exists. And then we can uniquely extend those to actual positive linear functionals that sends the one function to one. And then we can use the Ries-Markov representation theorem to identify those with Radon probability measures. So that's the idea here. Then for example 3, we look at the bounded Lipschitz monads on compact metric spaces. So this is the C for compact. So for a compact metric space, we can again look at the set of all Radon probability measures on X. And then we can give that a metric. So that metric is defined by this. So that's taking the supremum over all these difference of integrals where we integrate all the one Lipschitz functions. So this defines a metric, and we'll call that the bounded Lipschitz metric. And again, this gives us a functor curly L from compact metric spaces to compact metric spaces, and the morphisms we use in compact metric spaces are the one Lipschitz functions or the one Lipschitz maps. And then as before, we can define a unit and a multiplication. So in the same way, but you need to check, of course, that everything is one Lipschitz now. And then, yeah, this will define a monad. So we'll call the bounded Lipschitz monads. And this is very, very similar to the Kantorovich monad on compact metric spaces, but here I use a slightly different metric. So that's really the only difference there. So now I'll introduce something that looks maybe a bit strange, these singleton maps. So for a finite set, I'll call SA the family of all singletons and all co-singletons. And I'll call a map of finite sets a singleton map if the pre-image of every singleton or co-singleton is again a singleton or a co-singleton. And the category that that forms will denote by this. So the S for singleton and F for finite. And then as before, we can again look at all these probability measures on a finite set A, and we'll call that LA. And we can define a metric on that. So that's really the product metric. So that's defined by this. And then this will define a functor from these finite sets with singleton maps to compact metric spaces. Yeah, so and we need to have these singleton maps to make this work, to make this into a functor, but also for the result here, so that the codensity monad of L is the bounded Lipschitz monad. And the proof is very similar as the proof for the Radon monad, but the only thing here is you need to check that everything is one Lipschitz, and that can be difficult sometimes or causing some problems. And then a small remark, I could also have used the category of compact metric spaces with all Lipschitz maps. So not only the one Lipschitz maps. And then this space, curly LX, would be isomorphic to the Kantorovich space. And then as a final example, the Belle monad on the category of Hausdorff spaces. So again, I introduced these kind of maps between countable sets, in this case, very similar as the singleton maps. But here I'll take FA to be the collection of subsets of all finite and all cofinite subsets. And then I call a map between countable sets a finite map if the pre-image of every finite or cofinite set is again finite or cofinite. And the category we get from that, I'll denote by this. And then as before, we look at the probability measures on finite sets that will give us a functor from this category of countable sets. Yeah, so A is a countable set, so we use the category of countable sets and finite maps And then the codensity monad of this functor will be the monad of probability pair measures. So that's another kind of probability measure. Yes, and that was everything I had to say. Thank you.
Thank you, Ben, for your talk. And I'm looking for questions or comments from the audience.
Yeah, thank you for your talk. Very interesting. Could you please explain a little bit the comment about curly LX being isomorphic to the Cantorich space? Like in particular, does that mean that you can express the Cantorich monad also as a codensity monad?
So it's isomorphic to the Cantorich space in the case that that X is compact, so that's important, and that we use these all these Lipschitz maps. So yes, in that case, for the compact metric spaces in the category of all, where we use all Lipschitz maps, that should normally work.
Okay, very nice. Thank you.
There is another question in the audience. Some of your examples are actually strong monads. So can you say something about what properties of G, of a functor G, allow to derive that the monad that you get is strong, the codensity monad that you get is strong?
Yeah, I haven't really thought about that. So that's, I guess, if we have some monoidal structure on G and then the right Kahn extension of that preserves that in some way, I guess we can do something with that. But I haven't really thought about that.
So that seems to be all in the audience. How about other participants? Yeah,
thank you for the talk. That was very interesting. I kind of got the impression that you start off with the monads that you're interested in, and then you kind of construct a functor that has the property that the monad that you started off with is the codensity monad of that functor. If that is the case, then can you give some kind of intuition as to how, I mean, in each of these cases, you've constructed a different functor and you've obviously followed some procedure to construct that functor. Can you give some intuition as to how you would go about doing that, if that is the case? Thanks.
Yeah, so this small g is always the small, or the restriction of the curly g or other letters. So that's right. And the way all the proofs goes is to just define these integration operators. So that's in all the proofs the thing that happens. And then depending on which sets you use, you have either a finite additivity or a sigma additivity. And then depending on how nice the spaces are, you can correspond those with probability measures. I don't know if that was an answer to your question, maybe.
I mean, yeah, I guess I don't have that much intuition on the kind of analysis-y kind of side of all of this. So I'm just kind of trying to think, if you start off with a monad, how do you isolate what that kind of, it's usually maybe not a subcategory, but some kind of functor into your base. But yeah, maybe I'll just have to think about it. Yeah.
Yeah, sorry, I don't think I have a very specific answer to that, but thank you.
All good, no worries, thanks.
So what? Yeah, go on.
Sorry, should I ask my question?
Yes, do.
Thank you. Thanks for a nice talk. I was just wondering, and I may have missed this, is there some way of constructing these via some restriction in some sense of the ultrafilter monad or something? Because I got the sense that you're using, well, for example, with the bare space one, you were using like non-principal ultrafilters or something.
Maybe I did, but I then really didn't did it in an, didn't really think about it like that. So it is of course very similar to the ultra filter monad and I guess other filter monads in the sense that these codensity constructions give us like these linear functionals. But yeah, I couldn't really.
Sure. I was just thinking in terms of, because when you take cofinite finite sets, and that corresponds to like you have the cofinite sets forming a non-principal ultrafilter, for example.
I
like
see.
When you take like the Cantor space, for example, then cofinite sets are a non-principal ultrafilter. Anyway, just a thought. Thank you.
Yes, thank you. Sorry, I didn't really think about it in that way, but thank you.
Thank you.
So that seems to be all. No, it is not all. There is another participant. Thank you for the talk. I wanted to make a comment on the question of Adrian. There is a canonical candidate for the codensity monad, which is the full subcategory of fixed points. And if you think about it, this is precisely what happens with the ultrafilter monad, whose subcategory of fixed points are finite sets, right? And in my paper on codensity monads, I show that there is a morphism of monads between the subcategory generated by fixed points and the monad you start from. And in a sense, I conjectured that you can tell whether the monad is a good codensity monad, even only if this is an ISO, but I never managed to prove it. So if you are interested to this question, check it out. That's all.
Yeah, this was the paper you might have mentioned to me before. Maybe I'll look into that. Thank you, Ivan, for the reminder.
So I think the time has come to thank the speaker again.